What if the key to unlocking the mysteries of the universe lies not in the vastness of space, but in the tiniest particles that make up everything we know? Imagine a world where communication across billions of miles happens instantly, where the secrets of black holes are no longer hidden, and where humanity's reach into the cosmos is no longer limited by the speed of light. This isn't science fiction. This is the groundbreaking potential of quantum entanglement. Quantum entanglement, one of the most mysterious and mind-bending phenomena in physics, could revolutionize how we communicate in space. It's a concept so strange that even Einstein called it spooky action at a distance. But what if this spooky action could become the backbone of futuristic space communication? What if it could allow us to send messages faster than light, create unhackable networks, or even communicate across black holes? In this video, we're diving into 25 specific theories on how quantum entanglement could transform space communication as we know it. From enabling real-time communication with interstellar probes to creating secure quantum networks for space agencies, these ideas push the boundaries of what we thought was possible. We'll explore how entangled particles could help us navigate deep space, detect dark matter, and even communicate with extraterrestrial civilizations. By the end of this video, you'll not only understand the incredible potential of quantum entanglement, but also see how it could redefine humanity's future in space. So, if you're ready to explore the cutting edge of science and technology, stay tuned, because what you're about to discover might just change the way you see the universe forever. Now let's dive into the first theory: instantaneous communication across vast distances. Picture this: a spacecraft exploring the far reaches of our solar system, or even beyond, sending data back to Earth in real time. No delays, no waiting for hours or even years for a signal to travel across the void. Sounds impossible, right? But quantum entanglement might just make it a reality. Here's how it works. When two particles become entangled, their properties are linked, no matter how far apart they are. Change one, and the other changes instantly, faster than the speed of light. This phenomenon could allow us to create a communication system where information is shared instantaneously between Earth and distant space probes. Imagine a mission to Proxima Centauri, our nearest star system, where data from the probe reaches us the moment it's collected, without the usual light speed lag. The implications for interstellar missions are staggering. Real-time communication would mean scientists could adjust experiments, troubleshoot issues, and make critical decisions without the agonizing delays we face today. It could also open the door to more ambitious missions, like sending probes to explore exoplanets or even distant galaxies, knowing we can stay connected every step of the way. But it's not just about speed. This kind of communication could also enhance the safety and efficiency of space exploration. For example, if a probe encounters a problem, Earth-based teams could respond immediately, potentially saving the mission. And for future human colonies on Mars or beyond, instant communication could mean staying in touch with loved ones or receiving urgent updates without delay. Of course, there are challenges to overcome. Entangled particles are incredibly delicate, and maintaining their connection over such vast distances is no small feat. But if we can crack the code, the possibilities are endless. Quantum entanglement could redefine how we explore the cosmos, turning what once seemed like science fiction into science fact. And speaking of redefining possibilities, let's move on to the next theory: secure quantum communication networks. How could entangled particles create unhackable channels for space agencies? Stay tuned to find out. Now, let's shift our focus to another groundbreaking application of quantum entanglement: secure quantum communication networks. Imagine a world where sensitive data transmitted between Earth and distant spacecraft is completely immune to hacking or interception. Sounds like something out of a spy thriller, right? But with quantum entanglement, this could become a reality for space agencies. Here's the key idea. When particles are entangled, any attempt to intercept or measure them disrupts their delicate state. This means that if someone tries to eavesdrop on a quantum encrypted message, the act of tampering would immediately alert the sender and receiver. In other words, quantum communication is inherently secure. For space missions, this could be a game changer. Think about the kind of data we send and receive during interplanetary missions, scientific findings, navigation commands, even personal messages for astronauts. All of this information is vulnerable to interception or sabotage, especially as we venture further into space. But with quantum entanglement, we could create communication channels that are virtually unhackable. This would not only protect sensitive data, but also ensure the integrity of critical mission operations. For example, consider a Mars rover sending back high-resolution images of the planet's surface. If that data were intercepted or altered, it could lead to flawed scientific conclusions or even jeopardize the mission. But with quantum-secure communication, we could trust that the information is authentic and untampered. The benefits extend beyond just security. Unhackable communication networks could also foster greater collaboration between space agencies. Imagine international teams working together on missions to explore distant moons or asteroids, sharing data in real time without fear of cyberattacks. This level of trust and cooperation could accelerate our progress in space exploration. Of course, building such networks won't be easy. Quantum systems are incredibly sensitive, and maintaining entanglement over vast distances poses significant technical challenges. But the potential rewards are immense. Secure quantum communication could revolutionize how we share information in space, paving the way for safer, more efficient missions. And speaking of efficiency, let's turn our attention to the next theory, quantum entanglement for deep space navigation. How could entangled particles help spacecraft find their way through the cosmos? Stay tuned to find out. Now, let's venture into the fascinating realm of deep space navigation and how quantum entanglement could redefine the way spacecraft find their way through the cosmos. Picture this, a spacecraft millions of miles from Earth, navigating the vast emptiness of space with pinpoint accuracy. Sounds like science fiction, but quantum entanglement might just make it a reality. Here's how it works. Traditional navigation systems for spacecraft rely heavily on Earth-based signals, like those from the Deep Space Network. These signals take time to travel, especially over astronomical distances, which can lead to delays and inaccuracies. But entangled particles could change the game entirely. When particles are entangled, their states are linked no matter how far apart they are. This means that if one particle's state changes, the other instantly reflects that change, even across light years of space. By leveraging this phenomenon, spacecraft could use entangled particles as a kind of cosmic GPS. Imagine a spacecraft equipped with a quantum navigation system. It could generate entangled particles and keep one half on board while sending the other half back to Earth. As the spacecraft moves, changes in its position would affect the state of the entangled particles. Scientists on Earth could then measure these changes in real time, providing the spacecraft with precise location data without the delays of traditional communication. This approach could drastically reduce reliance on Earth-based systems, making deep space missions more autonomous and efficient. For example, a probe exploring the outer reaches of the solar system could navigate complex environments like asteroid fields or the gravitational fields of distant planets with unprecedented precision. But the benefits don't stop there. Quantum navigation could also enhance the safety of manned missions. Astronauts traveling to Mars or beyond would need accurate, real-time navigation to avoid hazards and ensure a safe journey. With entangled particles, they could receive instant updates on their position and trajectory. Even in the most remote corners of space, of course, there are challenges to overcome. Maintaining entanglement over such vast distances is no small feat. and the technology required to measure these subtle quantum states is still in its infancy. But the potential is undeniable. Quantum entanglement could revolutionize deep space navigation, making it faster, more accurate, and less dependent on Earth. And as we look ahead, the possibilities only grow more exciting. Up next, we'll explore how quantum repeaters could extend the reach of entangled communication, enabling seamless connections across the solar system. Stay tuned to uncover how this technology could bridge the gaps between worlds. Now, let's shift our focus to a groundbreaking concept that could solve one of the biggest challenges in quantum communication: distance. While quantum entanglement allows for instantaneous connections between particles, maintaining that connection over vast stretches of space is no easy task. This is where quantum repeaters come into play, offering a potential solution to extend the reach of entangled communication across the solar system and beyond. Quantum repeaters act as relay stations for entangled particles, effectively boosting their signal over long distances. Here's how it works. In traditional communication, signals weaken as they travel, requiring amplifiers to keep them strong. Similarly, entangled particles can lose their delicate quantum states over long distances due to interference or environmental factors. Quantum repeaters step in to preserve and extend these states, ensuring that the entanglement remains intact. Imagine a chain of quantum repeaters placed strategically between Earth and a distant spacecraft. Each repeater would receive entangled particles, measure their states, and then generate new entangled pairs to continue the connection. This process effectively refreshes the entanglement, allowing it to span much greater distances than would otherwise be possible. The implications for space communication are enormous. With quantum repeaters, we could establish a seamless quantum network across the solar system, enabling real-time communication between Earth and missions to Mars, the outer planets, or even interstellar probes. This would eliminate the frustrating delays caused by the speed of light, which currently limit how quickly we can send and receive data from distant spacecraft. For example, a Mars rover equipped with quantum communication technology could send high-resolution images and scientific data back to Earth instantly, rather than waiting minutes or hours for the signals to travel. Similarly, astronauts on a mission to Jupiter could communicate with mission control in real time, receiving immediate guidance and support during critical operations. But the potential doesn't stop at the solar system. Quantum repeaters could also pave the way for interstellar communication, allowing us to stay connected with probes sent to nearby star systems. This would revolutionize our ability to explore and understand the universe, providing a constant flow of data from the farthest reaches of space. Of course, building and deploying quantum repeaters is no small feat. The technology is still in its early stages, and significant challenges remain, such as maintaining the stability of entangled particles over long periods and ensuring the repeaters can operate reliably in the harsh conditions of space. However, the progress being made in quantum physics and engineering suggests that these hurdles are not insurmountable. As we continue to push the boundaries of quantum technology, the dream of a solar system-wide quantum communication network grows closer to reality. And with it comes the promise of faster, more reliable, and more secure connections that could transform how we explore and interact with the cosmos. Next, we'll dive into an even more speculative yet thrilling idea: how quantum entanglement might allow us to send information across black holes, potentially unlocking new frontiers in our understanding of spacetime. Stay tuned as we explore the cutting edge of quantum physics and its implications for the future of space exploration. Now, let's venture into one of the most mind-bending possibilities of quantum entanglement: its potential to enable communication across black holes. Black holes, those mysterious regions of spacetime where gravity is so intense that nothing, not even light, can escape, have long fascinated scientists and science fiction enthusiasts alike. But what if quantum entanglement could allow us to send information across these cosmic behemoths, challenging our understanding of physics itself? The idea hinges on the unique properties of entangled particles. As we've discussed, entangled particles share a connection that remains instantaneous, no matter how far apart they are. Now, imagine one of these particles falling into a black hole while its entangled partner remains outside. Could the particle outside the black hole still carry information about its counterpart inside? This question pushes the boundaries of our current knowledge, blending quantum mechanics with the strange physics of black holes. One speculative theory suggests that entangled particles could act as a kind of bridge across a black hole's event horizon, the point of no return. If this were possible, it might allow us to transmit information from inside the black hole to the outside universe, something previously thought to be impossible. This could revolutionize our understanding of space-time, offering new insights into how information behaves in extreme gravitational environments. However, this idea is not without its challenges. Black holes are known to destroy information, a phenomenon famously described by Stephen Hawking as the black hole information paradox. If entangled particles could somehow preserve or transmit information across a black hole, it would require a radical rethinking of this paradox and potentially lead to new theories that unify quantum mechanics and general relativity. While this concept remains highly speculative, it opens up exciting possibilities for the future of space exploration and communication. For instance, if we could harness entangled particles to interact with black holes, it might allow us to study these cosmic giants in unprecedented ways. We could gather data about the conditions inside a black hole, test theories about the nature of space-time, and even explore the possibility of wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe. Of course, the practical challenges are immense. Black holes are incredibly hostile environments, and the technology required to manipulate entangled particles in such extreme conditions is far beyond our current capabilities. But as we continue to explore the frontiers of quantum physics, the dream of using entanglement to unlock the secrets of black holes remains a tantalizing possibility. As we move forward, let's explore another fascinating application of quantum entanglement: how it could allow interstellar probes to send data back to Earth without degradation, even from light years away. This next theory could redefine our ability to explore distant star systems and bring the universe closer than ever before. Now, let's shift our focus to a groundbreaking application of quantum entanglement that could transform how we explore the cosmos, enabling interstellar probes to send data back to Earth without any loss of quality, even from distances spanning light years. Imagine sending a probe to a distant star system billions of miles away and receiving crystal-clear data in real time. Sounds like science fiction, right? But quantum entanglement might just make this a reality. Here's how it could work. Traditional communication methods like radio waves degrade over vast distances. The farther a probe travels, the weaker and more distorted its signals become. This limits how much information we can gather from distant missions, but entangled particles with their instantaneous connection could bypass this problem entirely. If a probe carried one half of an entangled pair and the other half remained on Earth, any change to the particle on the probe could instantly affect its partner here. This means data could be transmitted without the delays or degradation caused by distance. Think of it like this: instead of sending a message through space, which takes years to reach us, we'd be tapping into a shared connection that exists beyond the constraints of time and distance. This could allow interstellar probes to send high-resolution images, detailed scientific measurements, and even real-time updates from the farthest reaches of the galaxy. The implications for space exploration are staggering. We could study exoplanets, distant star systems, and even the edges of our galaxy with unprecedented clarity and speed. But there's a catch. While the idea is theoretically sound, the practical challenges are immense. Maintaining the entanglement of particles over such vast distances would require technology far beyond what we currently have. Any interference, whether from cosmic radiation or gravitational forces, could disrupt the entangled state. Plus, we'd need a way to encode and decode information using these particles, a process that's still in its infancy. Despite these hurdles, the potential rewards are too significant to ignore. If we could harness quantum entanglement for interstellar probes, it would revolutionize our ability to explore the universe. Missions that once took decades to yield results could provide real-time insights, opening up new frontiers in our understanding of the cosmos, and who knows? This technology might even pave the way for humanity's first steps into interstellar space. As we continue to push the boundaries of quantum physics, the dream of sending probes to distant stars and receiving instant, flawless data feels closer than ever. Next, let's explore how quantum entanglement could help us tackle another cosmic challenge: synchronizing clocks on spacecraft experiencing time dilation, a phenomenon that complicates coordination in the vastness of space. Now, let's turn our attention to another fascinating challenge in space exploration: time dilation. As spacecraft travel at incredibly high speeds or near massive objects like black holes, time doesn't tick the same way as it does on Earth. This phenomenon, predicted by Einstein's theory of relativity, means that clocks on these spacecraft could fall out of sync with those on Earth, creating a coordination nightmare for missions. But here's where quantum entanglement might come to the rescue. Imagine a spacecraft hurtling through space at near light speeds. For every second that passes on the spacecraft, several seconds might pass on Earth. This discrepancy might seem small, but over long missions, it could lead to significant misalignments in communication, navigation, and even scientific experiments. Traditional methods of synchronizing clocks struggle to account for these relativistic effects. However, entangled particles, with their unique ability to remain connected across vast distances, could offer a solution. Here's how it could work. If a spacecraft carried one half of an entangled pair and the other half stayed on Earth, changes to the particles could be used to compare the passage of time in both locations. Because entangled particles are instantaneously linked, any measurement of one particle would immediately reflect the state of its partner, regardless of the distance or time dilation effects. This could allow scientists to continuously adjust and synchronize the clocks on the spacecraft with those on Earth, ensuring precise coordination even in extreme relativistic environments. Think of it as having a cosmic stopwatch that never loses time. Whether a spacecraft is orbiting a black hole or traveling at a fraction of the speed of light, entangled particles could provide a real-time reference for timekeeping. This would be invaluable for missions requiring split-second precision, such as docking maneuvers, data collection, or even coordinating with other spacecraft in a fleet. Of course, this idea isn't without its challenges. Maintaining entanglement over such vast distances and under extreme conditions would require cutting-edge technology. Cosmic radiation, gravitational waves, and other space phenomena could disrupt the entangled state, making it difficult to rely on this method for long-term missions. Additionally, encoding and decoding time data using entangled particles would demand breakthroughs in quantum communication. Yet the potential benefits are immense. By solving the problem of time dilation, quantum entanglement could enable more ambitious missions to the farthest reaches of space. Imagine sending a probe to the edge of a black hole and receiving perfectly synchronized data, or coordinating a fleet of spacecraft exploring distant star systems with flawless precision. The possibilities are as vast as the universe itself. As we continue to explore the mysteries of quantum entanglement, the dream of overcoming time dilation feels increasingly within reach. Next, we'll dive into how entangled particles could revolutionize space-based quantum computing, unlocking new levels of processing power for missions beyond our solar system. Now, let's shift our focus to a groundbreaking application of quantum entanglement that could redefine the way we process information in space: space-based quantum computing. Picture this: a quantum computer orbiting Earth or traveling through the cosmos, harnessing the power of entangled particles to perform calculations at speeds that would make even the most advanced supercomputers on Earth seem sluggish. This isn't just science fiction, it's a potential reality that could transform space exploration as we know it. Quantum computers, unlike classical ones, rely on qubits, which can exist in multiple states simultaneously thanks to the principles of superposition and entanglement. When entangled particles are used as qubits, they can process vast amounts of data in parallel, solving complex problems in seconds that would take traditional computers years. Now, imagine deploying such a system in space. The benefits would be extraordinary. For starters, space-based quantum computers could analyze data from distant planets, stars, and galaxies in real time. Imagine a probe sending back terabytes of information from an exoplanet. A quantum computer in orbit could sift through this data instantly, identifying patterns, anomalies, or even signs of life that might otherwise go unnoticed. This would drastically reduce the time it takes to make groundbreaking discoveries, giving scientists the ability to react and adapt their missions on the fly. But the advantages don't stop there. Quantum entanglement could also enable these computers to communicate with each other across vast distances without the delays imposed by the speed of light. A network of quantum computers spread across the solar system could work together as a single, unified system, sharing data and processing power seamlessly. This would be a game-changer for missions requiring real-time decision-making, such as navigating asteroid fields or coordinating multiple spacecraft in a fleet. Of course, building and maintaining quantum computers in space comes with its own set of challenges. Cosmic radiation, extreme temperatures, and the vacuum of space could all interfere with the delicate quantum states needed for these systems to function. However, advancements in quantum error correction and shielding technologies are already paving the way for more robust quantum systems, and with entangled particles providing a foundation for both computation and communication, the potential for overcoming these hurdles is immense. The implications of space-based quantum computing are staggering, from accelerating the search for extraterrestrial life to enabling interstellar travel. This technology could open doors to possibilities we've only dreamed of. As we continue to push the boundaries of quantum science, the idea of a quantum-powered space age feels closer than ever. Next, we'll explore how entangled particles might help us detect one of the universe's greatest mysteries, dark matter. Stay tuned as we dive into the next frontier of quantum entanglement and its potential to unlock the secrets of the cosmos. Now, let's venture into one of the most enigmatic realms of the universe, dark matter. Imagine a substance that makes up roughly 85% of all matter in the cosmos, yet remains invisible to our current detection methods. This is the mystery of dark matter, and quantum entanglement might just hold the key to unraveling it. Here's how it could work. Dark matter doesn't interact with light or electromagnetic forces, which is why it's so difficult to detect. But what if entangled particles could act as a kind of cosmic sensor? When particles are entangled, their states are deeply connected, no matter how far apart they are. If dark matter interacts with one of these particles, even in the slightest way, it could disturb the entanglement. This disturbance could then be measured, providing us with a way to detect the presence of dark matter indirectly. Think of it like this: imagine you're in a pitch-black room and you can't see anything. But if you stretch out a spider web of threads across the room, you'd feel the slightest touch or vibration. Entangled particles could act like that spider web, picking up the faintest interactions with dark matter that would otherwise go unnoticed. The implications of this are enormous. detecting dark matter could help us understand the structure of the universe, from the formation of galaxies to the behavior of cosmic expansion. It could also provide clues about the nature of gravity itself, potentially bridging the gap between quantum mechanics and general relativity. But there's more. If we can detect dark matter using entangled particles, we could also study its properties. For instance, does dark matter clump together in certain regions of space? Does it interact with itself in ways we haven't yet imagined? These are questions that could reshape our understanding of the cosmos. Of course, this is still a theoretical concept, and there are significant challenges to overcome. Maintaining the stability of entangled particles in the harsh environment of space, for example, would require advanced shielding and error correction techniques. But with the rapid progress in quantum technology, the dream of using entanglement to detect dark matter is becoming more plausible every day. As we continue to explore the potential of quantum entanglement, the possibility of unlocking the secrets of dark matter feels tantalizingly close. And who knows, this could be the breakthrough that finally brings this invisible cosmic giant into the light. Next, we'll turn our attention to how entangled particles could help us predict space weather, protecting astronauts and equipment from the unpredictable forces of the cosmos. Stay with us as we dive into this fascinating application of quantum entanglement. Now, let's shift our focus to a critical challenge in space exploration: predicting space weather. Solar flares and cosmic radiation are among the most unpredictable and dangerous phenomena in the cosmos, capable of disrupting communication systems, damaging spacecraft, and posing serious risks to astronauts. But what if quantum entanglement could give us a new tool to forecast these events with greater accuracy? Here's the idea. Solar flares and cosmic radiation are driven by the sun's magnetic activity, which can be incredibly complex and difficult to monitor in real time. Traditional methods rely on satellites and telescopes to observe the sun's surface, but these tools have limitations. They can't always detect subtle changes in magnetic fields or predict when a flare might erupt. This is where entangled particles could come into play. Imagine a network of quantum sensors placed in orbit around the sun. These sensors would use entangled particles to detect minute changes in magnetic fields or radiation levels. Because entangled particles are deeply connected, any disturbance in one particle would instantly affect its partner, no matter how far apart they are. This instantaneous connection could allow us to detect early warning signs of solar activity much faster than current methods. Think of it like having a weather radar for space. Just as meteorologists use radar to track storms on Earth, quantum sensors could provide real-time data on solar flares and cosmic radiation. This data could then be used to create more accurate forecasts, giving astronauts and mission control teams precious time to prepare. For example, if a solar flare is detected, astronauts could take shelter in shielded areas of their spacecraft, and sensitive equipment could be powered down to avoid damage. The benefits don't stop there. Improved space weather prediction could also enhance the safety of satellites and space stations. Solar flares can interfere with satellite communications and navigation systems, causing disruptions on Earth. By predicting these events more accurately, we could minimize their impact, ensuring that critical infrastructure remains operational. Of course, there are challenges to overcome. Maintaining the stability of entangled particles in the harsh environment of space would require advanced technology and precise engineering. But with ongoing advancements in quantum science, the possibility of using entanglement for space weather prediction is becoming more realistic. As we continue to explore the potential of quantum entanglement, the ability to predict and mitigate the effects of space weather could revolutionize how we approach space exploration. It's not just about protecting astronauts and equipment. It's about ensuring the success and sustainability of missions that push the boundaries of human knowledge. Next, we'll explore how entangled particles could open the door to communication with extraterrestrial civilizations. a concept that challenges our understanding of the universe itself. Stay tuned as we dive into this mind-bending possibility. Now, let's venture into one of the most intriguing possibilities of quantum entanglement: communication with extraterrestrial civilizations. Imagine a scenario where humanity discovers intelligent life beyond our planet. The challenge: traditional methods of communication like radio waves are limited by the speed of light. Sending a message to a distant star system could take decades or even centuries to reach its destination, and the same goes for receiving a reply. But what if quantum entanglement could provide a way to bypass these limitations entirely? Here's how it might work. Entangled particles share a unique connection that allows them to influence each other instantaneously, regardless of the distance between them. If we could create a pair of entangled particles and send one half of the pair to an alien civilization, perhaps aboard a spacecraft or through some yet-to-be-discovered method, we could use the remaining particle on Earth to send and receive messages in real time. The moment we alter the state of our particle, the entangled particle light years away would instantly reflect that change, effectively creating a communication channel that defies the constraints of light speed delays. This idea isn't just science fiction. While we don't yet have the technology to entangle particles over interstellar distances, the concept is grounded in the principles of quantum mechanics. If extraterrestrial civilizations have also harnessed quantum entanglement, they might already be using it to communicate across the cosmos. This raises fascinating questions. Could we detect these quantum signals? And if so, how would we decode them? One of the biggest advantages of quantum communication with aliens is its security. Traditional signals like radio waves can be intercepted or jammed. But entangled particles are inherently secure. Any attempt to eavesdrop on the communication would disrupt the entanglement, alerting both parties to the intrusion. This makes quantum entanglement not only a potential tool for faster communication, but also a highly secure one. Of course, there are significant hurdles to overcome. For starters, we'd need to establish a shared framework for communication. How would we agree on a language or protocol with a civilization that might think and communicate in ways entirely different from our own? Additionally, the practical challenges of creating and maintaining entangled particles over such vast distances are immense. But as our understanding of quantum mechanics deepens, these obstacles may become surmountable. The implications of quantum entanglement for alien communication are profound. It could allow us to exchange knowledge, ideas, and even cultural insights with civilizations that might otherwise remain forever out of reach. This isn't just about sending a message, it's about building bridges across the cosmos, connecting humanity with other intelligent beings in ways we can barely imagine. As we ponder this possibility, it's worth considering how quantum entanglement could reshape our understanding of the universe. If we can communicate instantaneously with distant civilizations, what does that mean for our place in the cosmos? And what might we learn from beings who have mastered the mysteries of quantum physics long before us? Next, we'll explore how entangled particles could revolutionize connectivity between Earth and future space colonies, ensuring seamless collaboration across the stars. Stay with us as we uncover the next chapter in this quantum-powered future. Now, let's shift our focus to a more tangible and near-future application of quantum entanglement, connecting Earth with space colonies. As humanity sets its sights on establishing permanent settlements on the Moon, Mars, and beyond, one of the biggest challenges will be maintaining reliable communication across these vast distances. Traditional methods like radio signals face significant delays. For example, a message sent to Mars can take anywhere from 4 to 24 minutes to reach its destination, depending on the planet's positions. This lag makes real-time collaboration nearly impossible. But what if quantum entanglement could bridge this gap? Here's how it might work. Imagine a network of entangled particles linking Earth with a space colony on Mars. Each colony would have its own set of entangled particles paired with counterparts on Earth. When a message is sent, the state of the particle on Earth is altered, and its entangled partner on Mars instantly reflects that change. This would allow for instantaneous communication, eliminating the frustrating delays caused by the speed of light. The benefits of such a system are immense. For one, it would enable real-time decision-making between Earth and space colonies. Astronauts and colonists could consult with experts on Earth without waiting for responses, making missions safer and more efficient. It would also allow for seamless coordination of resources, scientific experiments, and even emergency responses. Picture a scenario where a Mars colony faces a critical issue, like a malfunctioning life support system. With quantum entanglement, they could instantly relay the problem to Earth, receive guidance, and implement solutions without losing precious time. But the potential goes beyond practical applications. Instant communication could foster a sense of connection between Earth and its off-world colonies. Families separated by millions of miles could share moments in real time, bridging the emotional distance as well as the physical one. This could be crucial for the mental well-being of colonists, who might otherwise feel isolated in the vastness of space. Of course, there are challenges to consider. Creating and maintaining entangled particles over such distances is no small feat. The technology required to entangle particles and keep them stable over long periods is still in its infancy. Additionally, the infrastructure needed to support a quantum communication network would be complex and costly. But as advancements in quantum technology continue, these hurdles may become surmountable. The implications of quantum entanglement for space colony connectivity are profound. It could transform how we explore and inhabit the cosmos, turning distant colonies into extensions of Earth rather than isolated outposts. This isn't just about faster communication. It's about creating a unified human presence across the solar system, where collaboration and connection are as seamless as they are on Earth. As we look ahead, it's exciting to imagine a future where quantum entanglement enables humanity to thrive beyond our home planet. But this is just one piece of the puzzle. Next, we'll explore an even more mind-bending possibility, using entangled particles to send information through wormholes, potentially enabling faster-than-light communication. Stay tuned as we dive into the next frontier of quantum-powered space exploration. Now, let's venture into one of the most fascinating and speculative ideas in quantum physics, the possibility of using entangled particles to send information through wormholes. This concept pushes the boundaries of our understanding of space, time, and communication, offering a glimpse into a future where faster-than-light communication might not just be science fiction. Wormholes, often depicted in popular media as shortcuts through space-time, are theoretical tunnels that could connect two distant points in the universe. While their existence remains unproven, they've long captured the imagination of scientists and storytellers alike. Now, imagine combining this idea with quantum entanglement. If entangled particles could somehow be linked through a wormhole, it might allow information to travel instantaneously across vast cosmic distances, bypassing the limitations imposed by the speed of light. Here's how this could theoretically work. Entangled particles share a unique connection where the state of one instantly influences the other, no matter how far apart they are. If these particles were positioned at either end of a wormhole, altering the state of one particle could cause an immediate change in its entangled counterpart on the other side. This would effectively create a communication channel that operates outside the constraints of traditional physics. The implications of such a system are staggering. For one, it could revolutionize interstellar travel and exploration. Imagine a spacecraft venturing into the far reaches of the galaxy, able to send real-time updates back to Earth through a wormhole-entangled network. This would eliminate the agonizing delays of conventional communication, allowing for instant coordination and decision-making, but the potential goes even further. If wormholes and quantum entanglement could be harnessed together, it might open the door to entirely new forms of communication. For instance, we could potentially send messages across galaxies, or even explore the idea of communicating with parallel universes, should they exist. This would not only transform our understanding of the cosmos, but also redefine what it means to be connected in a universe that's far more intricate than we ever imagined. Of course, this idea is still firmly in the realm of theory. Wormholes remain hypothetical, and the technology to create or stabilize them is far beyond our current capabilities. Similarly, maintaining entangled particles across such extreme conditions presents its own set of challenges. Yet, as our understanding of quantum mechanics and general relativity deepens, these once fanciful ideas may inch closer to reality. What makes this concept so compelling is its ability to inspire. It challenges us to think beyond the limits of our current knowledge and imagine a future where the boundaries of space and time are no longer barriers to communication. While the road to achieving such a feat is long and uncertain, the mere possibility fuels our curiosity and drives innovation in both physics and technology. As we ponder the potential of wormhole communication, it's clear that quantum entanglement continues to push the envelope of what's possible, but this is just one of the many ways it could reshape our future. Next, we'll explore how entangled particles could enable swarms of small spacecraft to communicate and coordinate efficiently, unlocking new possibilities for space exploration. Stay with us as we dive into the next chapter of this quantum-powered journey. Now, let's shift our focus to a concept that could redefine how we explore the cosmos: the use of quantum entanglement to coordinate swarms of small spacecraft. Imagine a fleet of tiny, interconnected probes working together like a well-oiled machine, each one seamlessly communicating with the others, even across vast distances. This is where quantum entanglement steps in, offering a revolutionary way to enhance coordination and efficiency in space exploration. Picture this: instead of relying on a single, large spacecraft, we deploy a swarm of smaller, more agile probes. These probes could cover more ground, gather diverse data, and adapt to unexpected challenges far more effectively than a single vessel. But here's the catch: how do you ensure that all these probes stay in sync, especially when they're spread out across millions of miles? That's where entangled particles come into play. By linking these spacecraft through entangled particles, we could create a communication network that operates instantaneously, no matter how far apart the probes are. Each spacecraft would carry an entangled particle, and any change in the state of one particle would instantly affect its counterpart on another probe. This would allow the swarm to share information, adjust their trajectories, and make collective decisions in real time without the delays imposed by traditional radio signals. The benefits of such a system are immense. For starters, it would enable more efficient exploration of distant planets, asteroids, and other celestial bodies. A swarm of probes could map an entire planet's surface, analyze its atmosphere, and search for signs of life, all while coordinating their efforts flawlessly. Additionally, this approach would make missions more resilient. If one probe encounters a problem, the others could quickly adapt, ensuring the mission's success isn't jeopardized. But the potential doesn't stop there. Quantum-entangled swarms could also revolutionize our ability to study dynamic cosmic events like supernova or black hole mergers. By positioning probes at different points in space, we could gather data from multiple angles simultaneously, providing a more comprehensive understanding of these phenomena. This could lead to groundbreaking discoveries that reshape our knowledge of the universe. Of course, there are challenges to overcome. Maintaining entanglement across such vast distances and in the harsh conditions of space is no small feat. We'd also need to develop advanced algorithms to manage the swarm's coordination and decision-making processes. Yet, as our understanding of quantum mechanics grows, so too does the feasibility of this idea. What makes this concept so exciting is its potential to unlock new frontiers in space exploration. By harnessing the power of quantum entanglement, we could create a new era of collaborative, efficient, and adaptive missions. It's a vision that not only pushes the boundaries of technology, but also inspires us to think bigger about what's possible in the cosmos. As we explore the possibilities of quantum-entangled spacecraft swarms, it's clear that this technology could be a game changer. But our journey through the quantum frontier doesn't end here. Next, we'll delve into how entangled particles could enhance our ability to detect gravitational waves, opening up new ways to study the universe's most dramatic events. Stay tuned as we continue to uncover the incredible potential of quantum entanglement in space communication. Now, let's turn our attention to another groundbreaking application of quantum entanglement: its potential to revolutionize the way we detect gravitational waves. Gravitational waves, those ripples in the fabric of space-time caused by massive cosmic events like black hole collisions or neutron star mergers, have already transformed our understanding of the universe. But what if we could detect them with even greater precision and sensitivity? That's where quantum entanglement comes into play. Imagine a scenario where entangled particles are used to enhance the sensitivity of gravitational wave detectors. These detectors, like the Laser Interferometer Gravitational Wave Observatory, or LIGO, rely on incredibly precise measurements of tiny changes in distance caused by passing gravitational waves. However, even the most advanced detectors face limitations due to quantum noise, a fundamental barrier that affects the accuracy of their measurements. This is where quantum entanglement offers a solution. By entangling the photons used in the detector's laser beams, we could reduce the impact of quantum noise, allowing for more precise measurements. Here's how it works. Entangled photons share a unique connection, meaning any change in one photon instantly affects its entangled partner. This property could be harnessed to cancel out noise and amplify the signal from gravitational waves, making it easier to detect even the faintest ripples in space-time. The implications of this are profound. With enhanced sensitivity, we could detect gravitational waves from events that are currently beyond our reach, such as those occurring in the early universe or from smaller, less energetic cosmic collisions. This would open up entirely new avenues for studying the cosmos, providing insights into phenomena like the formation of supermassive black holes, the nature of dark matter, and the very origins of the universe itself. Moreover, quantum-entangled detectors could help us map the universe in unprecedented detail. By pinpointing the sources of gravitational waves with greater accuracy, we could create a more comprehensive picture of cosmic events and their distribution across space and time. This could lead to discoveries that challenge our current understanding of physics and cosmology, pushing the boundaries of human knowledge. Of course, integrating quantum entanglement into gravitational wave detection is no small task. It requires overcoming significant technical challenges, such as maintaining entanglement over long distances and in the presence of environmental interference. But as our mastery of quantum technologies advances, the feasibility of this approach grows, bringing us closer to a new era of gravitational wave astronomy. What makes this idea so compelling is its potential to deepen our connection to the universe. By leveraging the power of quantum entanglement, we could unlock secrets hidden in the fabric of space-time, revealing the cosmic symphony that surrounds us. It's a vision that not only enhances our scientific capabilities, but also inspires us to explore the unknown with renewed curiosity and wonder. As we consider the possibilities of quantum-entangled gravitational wave detection, it's clear that this technology could transform our understanding of the cosmos. But our exploration of quantum entanglement's potential doesn't stop here. Next, we'll dive into how entangled particles could pave the way for a space-based quantum internet, offering ultra-fast and secure communication for future interplanetary civilizations. Stay tuned as we continue to uncover the incredible ways quantum entanglement could reshape our future in space. Now, let's shift our focus to a concept that could redefine how we connect across the cosmos: the idea of a quantum entangled space internet. Imagine a future where communication between Earth, Mars, and even distant space colonies is not only instantaneous but also completely secure. This is the promise of a space-based quantum internet powered by the extraordinary properties of entangled particles. At its core, a quantum internet would rely on the phenomenon of entanglement to transmit information. Unlike traditional internet signals, which are limited by the speed of light and vulnerable to interception, quantum entangled communication would be immune to these constraints. Here's why: when two particles are entangled, any change to one particle instantly affects the other, no matter how far apart they are. This means data could be transmitted across vast distances without the delays or risks associated with conventional methods. One of the most exciting applications of this technology is its potential to connect future space colonies. Picture a scenario where astronauts on Mars or a lunar base need to communicate with Earth in real time. With a quantum entangled network, they could send and receive data instantly, enabling seamless collaboration and decision-making. This would be a game-changer for missions that require precise coordination, such as scientific experiments or emergency responses. But the benefits don't stop there. A quantum space internet could also revolutionize global communication here on Earth. By extending the network into orbit, we could create a system that bypasses the limitations of terrestrial infrastructure, such as undersea cables or satellite latency. This would mean faster, more reliable internet access for remote areas, as well as enhanced security for sensitive data transmissions. Security, in fact, is one of the most compelling advantages of a quantum internet. Because entangled particles cannot be intercepted or copied without disrupting their state, any attempt to hack the system would be immediately detectable. This makes quantum communication virtually unhackable, offering a level of protection that's impossible with current technologies. Of course, building a quantum entangled space internet is no small feat. It would require overcoming significant challenges, such as maintaining entanglement over astronomical distances and developing the infrastructure to support such a network. However, recent advancements in quantum technology suggest that these hurdles are not insurmountable. As we continue to refine our understanding of entanglement and its applications, the dream of a space-based quantum internet becomes increasingly within reach. What makes this idea so transformative is its potential to unite humanity across the stars. By enabling instant, secure communication between Earth and distant worlds, a quantum internet could foster collaboration, innovation, and exploration on an unprecedented scale. It's a vision that not only pushes the boundaries of technology, but also inspires us to imagine a future where the vastness of space is no longer a barrier to connection. As we explore the possibilities of a quantum entangled space internet, it's clear that this technology could revolutionize how we communicate both on Earth and beyond. But our journey through the potential of quantum entanglement doesn't end here. Next, we'll delve into an even more speculative idea: the possibility of using entangled particles to send messages across parallel universes. Stay tuned as we continue to uncover the extraordinary ways quantum entanglement could reshape our understanding of reality itself. Now, let's venture into a realm that stretches the very fabric of our imagination: the idea of using quantum entanglement to communicate across parallel universes. This concept, while speculative, opens the door to possibilities that challenge our understanding of reality itself. Imagine a scenario where entangled particles could serve as a bridge between our universe and others, allowing us to send and receive information across dimensions. At the heart of this theory lies the idea that entangled particles might retain their connection not just across vast distances in our universe, but potentially across different universes altogether. If this were possible, it could mean that changes to a particle in one universe could instantaneously affect its entangled counterpart in another. This would allow for a form of communication that transcends the boundaries of space and time as we know it. While this idea might sound like science fiction, it's rooted in some of the most intriguing theories in modern physics. For instance, the multiverse hypothesis suggests that our universe is just one of many, each with its own unique set of physical laws and constants. If entangled particles can indeed interact across these universes, it could provide a way to test the existence of parallel realities and even exchange information with them. One of the most fascinating implications of this theory is its potential to revolutionize our understanding of physics. By enabling communication across universes, we could gain insights into the fundamental nature of reality, such as whether the laws of physics are consistent across all dimensions or if they vary in ways we can't yet comprehend. This could lead to groundbreaking discoveries that reshape our understanding of the cosmos. Of course, the challenges of achieving multiverse communication are immense. For one, we would need to find a way to create and maintain entanglement across universes, which is far beyond our current technological capabilities. Additionally, even if such communication were possible, interpreting the data from another universe would require a deep understanding of its unique physical laws, which could be vastly different from our own. Despite these hurdles, the idea of multiverse communication pushes the boundaries of what we consider possible. It invites us to think beyond the confines of our universe and explore the potential for connection in ways we've never imagined. Whether or not this becomes a reality, the pursuit of such ideas drives innovation and inspires us to question the limits of science and technology. As we ponder the possibilities of quantum entanglement and multiverse communication, it's clear that this theory represents one of the most ambitious and thought-provoking applications of quantum physics. It challenges us to rethink our place in the cosmos and consider the potential for connection not just across space, but across realities. With this mind-bending concept in mind, let's turn our attention to another practical application of quantum entanglement: its potential to monitor the health of spacecraft in real time. Stay tuned as we explore how entangled particles could revolutionize the way we maintain and operate missions in the vast expanse of space. Now, shifting our focus to a more practical yet equally groundbreaking application, let's explore how quantum entanglement could transform the way we monitor the health of spacecraft. Imagine a scenario where every critical system on a spacecraft, from its engines to its life support, is constantly monitored in real time, with instant alerts sent back to Earth the moment an issue arises. This isn't just a futuristic dream, it's a possibility that quantum entanglement could make a reality. At the core of this idea is the ability of entangled particles to share information instantaneously, no matter the distance. By embedding entangled particles into the systems of a spacecraft, we could create a network that continuously tracks the status of every component. For example, if a temperature sensor on a spacecraft detects overheating, its entangled counterpart on Earth would immediately reflect this change, allowing engineers to respond in real time. This would eliminate the delays caused by traditional communication methods, which rely on signals traveling at the speed of light. The implications for spacecraft health monitoring are immense. Currently, diagnosing and addressing issues on missions can take hours, days, or even longer, depending on the distance from Earth. With quantum entanglement, we could detect problems as they happen, enabling faster and more precise interventions. This could be especially critical for long-duration missions, such as those to Mars or beyond, where even minor malfunctions could jeopardize the entire mission. Beyond diagnostics, this technology could also enhance predictive maintenance. By analyzing the data from entangled particles, we could identify patterns that indicate wear and tear before a system fails. This proactive approach would not only extend the lifespan of spacecraft, but also reduce the risk of catastrophic failures, ensuring the safety of astronauts and the success of missions. Of course, implementing this technology comes with its own set of challenges. Creating and maintaining entanglement over such vast distances requires advancements in quantum engineering that we're still working toward. Additionally, integrating entangled systems into spacecraft designs would demand new protocols and infrastructure to handle the massive amounts of data generated. Despite these hurdles, the potential benefits make this a compelling area of research. Real-time health monitoring powered by quantum entanglement could revolutionize space exploration, making missions safer, more efficient, and more reliable. It's a testament to how quantum physics, once confined to the realm of theory, is now paving the way for practical innovations that could redefine our capabilities in space. As we consider the transformative potential of this technology, it's clear that quantum entanglement isn't just about pushing the boundaries of science. It's about solving real-world challenges in ways we've never imagined. And with that, let's turn our attention to another exciting frontier: how quantum entanglement could enhance our exploration of distant exoplanets. Stay tuned as we uncover the possibilities of this next groundbreaking application. Now, let's venture into the realm of distant worlds and uncover how quantum entanglement could revolutionize our exploration of exoplanets. Imagine sending a probe to a planet light years away, only to receive crystal-clear data in real time, as if the planet were just next door. This isn't science fiction, it's a potential reality made possible by the unique properties of entangled particles. At the heart of this idea lies the challenge of transmitting data across unimaginable distances. Traditional methods rely on radio signals, which, while effective, are limited by the speed of light. This means that data from a probe orbiting an exoplanet could take years or even decades to reach Earth. But with quantum entanglement, we could bypass this limitation entirely. By entangling particles on the probe with counterparts on Earth, we could create a direct communication link that transmits data instantaneously, no matter how far apart the 2 points are. This breakthrough would transform our ability to study exoplanets in unprecedented detail. For instance, high-resolution images of an exoplanet's surface, atmospheric readings, or even signs of potential life could be sent back to Earth without delay. Scientists could analyze this data in real time, making immediate decisions about where to focus their research or even guiding the probe to explore specific areas of interest. Moreover, quantum entanglement could enhance the quality of the data itself. Traditional signals degrade over long distances, losing clarity and precision. Entangled particles, however, maintain their connection, ensuring that the data arrives intact and unaltered. This would allow us to capture finer details, such as subtle changes in an exoplanet's atmosphere or the faint traces of organic molecules, which might otherwise be lost in transmission. The implications for exoplanet exploration are profound. With real-time, high-fidelity data, we could accelerate our search for habitable worlds, study the diversity of planetary systems, and even uncover clues about the origins of life in the universe. Missions that once took decades to yield meaningful results could now provide actionable insights in a fraction of the time. Of course, this technology isn't without its challenges. Maintaining entanglement over such vast distances requires overcoming significant technical hurdles, and integrating entangled systems into spacecraft designs would demand innovative engineering solutions. Yet, as we continue to push the boundaries of quantum physics, the dream of instant, flawless communication with distant worlds grows ever closer to reality. As we look to the stars, it's clear that quantum entanglement could be the key to unlocking the secrets of the cosmos. By bridging the gap between Earth and distant exoplanets, this technology could redefine our understanding of the universe and our place within it. And with that, let's turn our gaze to another fascinating application: how quantum entanglement could enhance the capabilities of space-based telescopes, bringing the wonders of the universe into sharper focus than ever before. Now let's shift our focus to the skies above and explore how quantum entanglement could transform the way we observe the universe through space-based telescopes. Picture this, a telescope orbiting Earth, capturing images of distant galaxies with such clarity that it feels like we're peering through a window into the cosmos. Quantum entanglement could make this vision a reality by enhancing both the resolution and data transmission capabilities of these powerful instruments. Traditional space telescopes like the Hubble or James Webb rely on light and electromagnetic waves to gather data. While these tools have revolutionized our understanding of the universe, they are still bound by the limitations of light speed and signal degradation over vast distances. Quantum entanglement offers a way to overcome these challenges. By entangling particles on the telescope with counterparts on Earth, we could create a direct, instantaneous link for transmitting data. This means that high-resolution images and complex astronomical data could be sent back to Earth without any delay or loss of quality. One of the most exciting possibilities is the improvement in resolution. Quantum entanglement could allow telescopes to capture finer details than ever before. Imagine being able to see the surface of an exoplanet in stunning detail, or observing the intricate structures of distant nebulae with unprecedented clarity. This level of precision could lead to groundbreaking discoveries such as identifying Earth-like planets, studying the formation of stars and galaxies, or even detecting subtle changes in the fabric of space-time. Another advantage lies in data transmission. Traditional methods often result in data loss or corruption, especially when transmitting over long distances. Entangled particles, however, maintain their connection regardless of distance, ensuring that the data arrives intact. This would allow astronomers to analyze raw, unaltered data in real time, making it easier to spot anomalies or unexpected phenomena. For example, a sudden burst of gamma rays or the faint glow of a distant quasar could be detected and studied immediately, providing valuable insights into the nature of these cosmic events. The implications for astronomy are immense. With quantum-enhanced telescopes, we could explore the universe in ways that were previously unimaginable. Missions designed to study dark energy, map the cosmic microwave background, or search for signs of extraterrestrial life could benefit from the increased precision and efficiency of entangled communication. This technology could also pave the way for collaborative efforts between multiple telescopes, creating a network of observatories that work together to capture a more comprehensive view of the cosmos. Of course, integrating quantum entanglement into space-based telescopes is no small feat. It would require advancements in quantum technology, as well as innovative engineering solutions to ensure the stability and reliability of entangled systems in the harsh environment of space. But as we continue to push the boundaries of science and technology, the potential rewards are too great to ignore. As we look to the future, it's clear that quantum entanglement could revolutionize not just how we communicate across space, but also how we observe and understand the universe itself. By enhancing the capabilities of space-based telescopes, this technology could bring us closer than ever to answering some of the most profound questions about our place in the cosmos. And with that, let's turn our attention to another intriguing application: how quantum entanglement could help us map the fabric of space-time, unlocking new insights into the mysteries of the universe. Now, let's venture into the fascinating realm of space-time itself and explore how quantum entanglement could revolutionize our ability to map its intricate fabric. Imagine being able to chart the very structure of the universe, from the subtle ripples of gravitational waves to the vast cosmic web that connects galaxies across billions of light years. Quantum entanglement could provide the tools to make this vision a reality, offering unprecedented insights into the nature of space and time. At the heart of this idea is the concept that entangled particles share a unique connection, one that remains intact regardless of the distance between them. This property could be harnessed to create a kind of quantum ruler capable of measuring the distortions and curves in space-time caused by massive objects like black holes, neutron stars, or even the remnants of the Big Bang. By placing entangled particles in strategic locations, say, on satellites orbiting Earth or deep space probes, we could detect and map these distortions with incredible precision. One of the most exciting applications of this technology lies in the study of gravitational waves. These ripples in space-time, first detected in 2015, are caused by cataclysmic events like the collision of black holes or neutron stars. While current detectors like LIGO and Virgo have opened a new window into the universe, they are limited by their sensitivity and the need for massive infrastructure. Quantum entanglement could enhance these detectors by providing a more sensitive and scalable way to measure gravitational waves. Entangled particles could act as ultra-precise sensors, detecting even the faintest distortions in space-time and allowing us to observe events that were previously beyond our reach. Another intriguing possibility is the mapping of the cosmic web, the vast network of dark matter and galaxies that forms the backbone of the universe. By using entangled particles to measure the gravitational effects of dark matter, we could create detailed maps of this invisible structure. This would not only deepen our understanding of how galaxies form and evolve, but also shed light on the mysterious nature of dark matter itself. Imagine being able to see the hidden scaffolding of the universe, revealing the forces that shape its growth and expansion over billions of years. Quantum entanglement could also play a crucial role in studying the early universe. By mapping the faint imprints left by the Big Bang on the fabric of space-time, we could gain new insights into the origins of the cosmos. For instance, entangled particles could help us detect primordial gravitational waves, which are thought to carry information about the universe's first moments. This could provide clues about the nature of inflation, the rapid expansion that occurred just after the Big Bang, and even help us test theories about the multiverse. Of course, the challenges of implementing this technology are significant. Maintaining the stability of entangled particles over vast distances and in the harsh conditions of space would require groundbreaking advancements in quantum engineering. But the potential rewards are immense. By mapping the fabric of space-time with quantum precision, we could unlock new frontiers in our understanding of the universe, from the smallest scales of quantum mechanics to the largest structures in the cosmos. As we continue to push the boundaries of science, quantum entanglement offers a powerful tool for exploring the mysteries of space and time. From gravitational waves to the cosmic web, this technology could transform our ability to observe and understand the universe, bringing us closer than ever to answering some of the most profound questions about existence itself. And with that, let's turn our attention to another groundbreaking application: how quantum entanglement could optimize energy efficiency in spacecraft, extending their capabilities and mission durations. Now, let's shift our focus to a practical yet revolutionary application of quantum entanglement: optimizing energy efficiency in spacecraft. Imagine a future where missions to distant planets or deep space are no longer constrained by the limitations of power supply. Quantum entanglement could hold the key to making this vision a reality, transforming how spacecraft manage and conserve energy. At the core of this idea is the ability of entangled particles to share information instantaneously, regardless of distance. This unique property could be harnessed to create highly efficient energy management systems for spacecraft. For instance, entangled particles could be used to monitor and regulate power consumption in real time, ensuring that every watt of energy is used as effectively as possible. By placing entangled sensors throughout a spacecraft, we could create a network that constantly adjusts energy distribution based on the needs of different systems, from propulsion to life support. One of the most significant challenges in space exploration is the limited availability of energy sources. Solar panels, for example, become less effective as spacecraft travel farther from the sun, and traditional fuel-based systems add weight and complexity. Quantum entanglement could help overcome these challenges by enabling more precise control over energy usage. For example, entangled particles could be used to optimize the operation of ion drives, which are highly efficient but require careful management of power. By fine-tuning the energy input to these drives using entangled sensors, we could extend their operational lifespan and reduce the overall energy consumption of the spacecraft. Another exciting possibility is the use of entangled particles to enhance the efficiency of energy storage systems. Batteries and other storage devices are critical for powering spacecraft during periods when solar energy is unavailable, such as during long missions to the outer planets or when traveling through the shadow of a celestial body. Quantum entanglement could improve the performance of these systems by providing real-time data on their condition and energy levels. This would allow for more accurate predictions of energy needs and better management of power reserves, ensuring that spacecraft can operate for longer periods without running out of energy. Quantum entanglement could also play a role in reducing the energy demands of communication systems. Transmitting data across vast distances in space requires significant power, especially for high-bandwidth signals. By using entangled particles to create more efficient communication protocols, we could reduce the energy required for data transmission. This would not only extend the operational life of spacecraft, but also enable more frequent and detailed communication with Earth, enhancing the scientific return of missions. Of course, implementing these technologies would require significant advancements in quantum engineering and space technology. Maintaining the stability of entangled particles in the harsh environment of space, for example, is a major challenge. However, the potential benefits are immense. By optimizing energy usage in spacecraft, we could extend mission durations, reduce costs, and enable more ambitious exploration of the solar system and beyond. As we continue to push the boundaries of space exploration, quantum entanglement offers a powerful tool for overcoming one of the most fundamental challenges: energy efficiency. From optimizing propulsion systems to enhancing communication protocols, this technology could revolutionize how we power and operate spacecraft, opening up new possibilities for discovery and exploration. And with that, let's turn our attention to another critical application: how quantum entanglement could improve the tracking and management of space debris, ensuring safer and more sustainable space travel. Now let's venture into a critical yet often overlooked aspect of space exploration: the growing challenge of space debris. With thousands of defunct satellites, spent rocket stages, and fragments orbiting Earth, the risk of collisions has become a pressing concern. But what if quantum entanglement could offer a solution to this problem, making space travel safer and more sustainable? At the heart of this idea is the ability of entangled particles to provide real-time, highly accurate data about the position and movement of objects in space. Traditional tracking systems rely on radar and optical sensors, which, while effective, have limitations in precision and coverage. Quantum entanglement could revolutionize this process by enabling a network of entangled sensors to monitor space debris with unprecedented accuracy. These sensors, placed on satellites or ground-based stations, could instantly share information about the location and trajectory of debris, creating a dynamic and constantly updated map of Earth's orbit. One of the key advantages of using entangled particles for debris tracking is their ability to operate independently of external signals. Unlike traditional systems, which can be affected by interference or signal delays, entangled sensors would provide instantaneous updates. This would allow spacecraft to make split-second adjustments to their paths, avoiding potential collisions with debris. For example, if a piece of debris were detected on a collision course with a satellite, the entangled network could alert the satellite's navigation system in real time, enabling it to maneuver out of harm's way. Another exciting possibility is the use of entangled particles to predict the future movement of space debris. By analyzing the data collected from entangled sensors, we could develop advanced algorithms to forecast the paths of debris over time. This would not only help in avoiding collisions, but also in planning the safe disposal of defunct satellites and other objects. For instance, mission planners could use this information to guide satellites into controlled re-entry paths, reducing the risk of creating additional debris. Quantum entanglement could also enhance the coordination of international efforts to manage space debris. Currently, tracking and mitigation efforts are fragmented, with different countries and organizations using their own systems. An entangled network could provide a unified global platform for sharing data, enabling more effective collaboration. This would be particularly valuable in crowded regions of space, such as low Earth orbit, where the risk of collisions is highest. Of course, implementing such a system would require overcoming significant technical challenges. Maintaining the stability of entangled particles in the harsh environment of space, for example, is no small feat. Additionally, developing the infrastructure to support a global network of entangled sensors would require substantial investment and international cooperation. However, the potential benefits are immense. By improving our ability to track and manage space debris, we could significantly reduce the risks to spacecraft, satellites, and even future space stations, ensuring safer and more sustainable space travel for generations to come. As we look to the future of space exploration, quantum entanglement offers a promising tool for addressing one of its most pressing challenges. From real-time collision avoidance to global collaboration, this technology could transform how we manage the growing problem of space debris, paving the way for safer and more efficient missions. And with that, let's turn our attention to another groundbreaking application: how quantum entanglement could enhance communication between space-based artificial intelligence systems, enabling smarter and faster decision-making in the cosmos. Now, shifting our focus to the realm of artificial intelligence in space, let's explore how quantum entanglement could revolutionize the way AI systems communicate and collaborate across the cosmos. Imagine a future where space-based AI systems, tasked with managing complex missions or analyzing vast amounts of data, can communicate instantaneously regardless of the distances involved. This is where quantum entanglement steps in as a game changer. At its core, quantum entanglement could enable AI systems to share information in real time, breaking free from the limitations imposed by the speed of light. Traditional communication methods, even those using advanced radio waves or lasers, face delays when transmitting data across vast interstellar distances. But with entangled particles, AI systems could exchange data instantaneously, allowing for seamless coordination and decision-making. For instance, a swarm of AI-driven probes exploring a distant planet could share their findings with each other and with a central command system without any lag, enabling them to adapt their strategies on the fly. One of the most exciting applications of this technology lies in the field of autonomous space exploration. AI systems equipped with quantum entangled communication capabilities could make split-second decisions based on real-time data from multiple sources. Picture a scenario where a space telescope detects a sudden cosmic event, like a supernova or a gamma-ray burst. With entangled communication, the telescope could instantly relay this information to nearby probes or satellites, which could then adjust their instruments to capture additional data. This level of coordination would significantly enhance our ability to study rare and fleeting astronomical phenomena. Moreover, quantum entanglement could empower AI systems to work together more effectively in complex missions. For example, during a mission to explore an asteroid, multiple AI-driven rovers could use entangled particles to share their observations and coordinate their movements. If one rover encounters an obstacle, it could instantly inform the others, allowing them to reroute and continue their exploration without interruption. This kind of real-time collaboration would not only improve efficiency but also reduce the risk of mission failure. another potential benefit is the ability of entangled AI systems to process and analyze data collectively. In space where resources are limited, distributing computational tasks across multiple AI units could be a game changer. By leveraging entangled particles, these systems could pool their processing power, enabling them to tackle complex problems that would be impossible for a single unit to handle alone. This could be particularly useful for tasks like mapping uncharted regions of space or simulating the behavior of distant celestial bodies. Of course, integrating quantum entanglement into space-based AI systems is not without its challenges. Maintaining the stability of entangled particles over long distances and in the harsh conditions of space would require significant advancements in technology. Additionally, developing the algorithms and protocols needed to manage entangled communication networks would be a complex undertaking. However, the potential rewards are immense. By enabling faster, more efficient communication between AI systems, quantum entanglement could unlock new possibilities for space exploration, from autonomous missions to advanced scientific research. As we continue to push the boundaries of what's possible in space, the fusion of quantum entanglement and artificial intelligence offers a glimpse into a future where machines work together seamlessly, making smarter and faster decisions in the vast expanse of the cosmos. And with that, let's turn our attention to the final theory in our exploration: how quantum entanglement could redefine the very future of space exploration, opening doors to new frontiers and possibilities. Now, as we reach the culmination of our journey through the transformative potential of quantum entanglement, let's take a moment to reflect on how this phenomenon could redefine the very future of space exploration. Quantum entanglement isn't just a scientific curiosity, it's a key that could unlock entirely new frontiers, reshaping how we explore, understand, and interact with the cosmos. At its heart, quantum entanglement offers a way to overcome some of the most significant challenges in space communication and exploration. By enabling instantaneous data transfer across vast distances, it could eliminate the delays that currently hinder our ability to explore deep space in real time. Imagine a future where missions to distant planets, moons, or even other star systems are guided by AI systems that communicate seamlessly, making decisions based on up-to-the-moment information. This could revolutionize everything from planetary exploration to the search for extraterrestrial life. One of the most profound implications of quantum entanglement lies in its ability to connect humanity with the farthest reaches of the universe. Future space colonies, whether on Mars, the Moon, or beyond, could maintain instant communication with Earth, fostering collaboration and ensuring the safety of astronauts. This level of connectivity would not only make long-term space habitation more feasible, but also open the door to entirely new forms of scientific research and discovery. Moreover, quantum entanglement could enable us to explore regions of space that are currently beyond our reach. For instance, entangled particles could allow us to study black holes, wormholes, or even the edges of the observable universe in ways that were previously unimaginable. By providing a way to transmit information across these extreme environments, quantum entanglement could help us unravel some of the universe's greatest mysteries, from the nature of dark matter to the origins of the cosmos itself. But the impact of quantum entanglement extends beyond just exploration. It could also transform how we approach space technology. From enhancing the capabilities of space-based telescopes to improving the efficiency of spacecraft, the applications are virtually limitless. By integrating entangled particles into our technology, we could create systems that are faster, smarter, and more resilient, paving the way for missions that push the boundaries of what we thought was possible. Of course, realizing this future will require overcoming significant challenges, from stabilizing entangled particles in the harsh conditions of space to developing the infrastructure needed to support quantum communication networks. There's still much work to be done. But the potential rewards are immense. quantum entanglement could not only redefine space exploration, but also inspire a new era of innovation, collaboration, and discovery. As we look to the stars, it's clear that quantum entanglement holds the promise of a brighter, more connected future. By harnessing this extraordinary phenomenon, we could unlock new possibilities, explore uncharted territories, and deepen our understanding of the universe. The journey ahead is filled with challenges, but also with incredible opportunities, and quantum entanglement could be the key that helps us seize them. So, as we conclude this exploration, let's keep our eyes on the horizon, where the future of space exploration is waiting to be discovered. As we bring this journey to a close, let's take a moment to revisit the incredible possibilities we've explored. From instantaneous communication across vast distances to secure quantum networks, the 25 theories we've discussed paint a vivid picture of how quantum entanglement could revolutionize space communication. Each idea, whether it's using entangled particles for deep space navigation or creating a quantum entangled space internet, highlights the transformative potential of this phenomenon. These theories aren't just science fiction, they're glimpses into a future where the boundaries of space and time are no longer obstacles to exploration and discovery. Quantum entanglement could redefine how we connect with the cosmos, enabling real-time communication with distant probes, enhancing the safety of astronauts, and even opening the door to interstellar collaboration. Imagine a world where space colonies on Mars or the Moon stay seamlessly connected to Earth, where swarms of spacecraft work together with perfect coordination, or where we can study black holes and wormholes in ways that were once thought impossible. The possibilities are as vast as the universe itself, but beyond the technical advancements, quantum entanglement represents something even greater, a shift in how we think about our place in the cosmos. It challenges us to dream bigger, to push the limits of what's possible, and to embrace the unknown with curiosity and courage. The future of space exploration isn't just about reaching new destinations, it's about reimagining how we explore, communicate, and understand the universe. As we look ahead, one thing is clear: quantum entanglement holds the key to unlocking a new era of discovery. The road ahead is filled with challenges, but also with incredible opportunities. By harnessing this extraordinary phenomenon, we could transform not only space communication, but also our understanding of the universe itself. The stars are calling, and quantum entanglement might just be the tool we need to answer that call. So, what do you think? Could quantum entanglement be the breakthrough that takes space exploration to the next level? Share your thoughts in the comments below. I'd love to hear your ideas and predictions. And if you enjoyed this deep dive into the future of space communication, don't forget to hit that like button, subscribe to the channel, and turn on notifications so you never miss out on more futuristic content. The universe is full of mysteries waiting to be uncovered, and together we can explore them all. Until next time, keep looking up. The future is closer than you think.